Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. Dear friends, during the last session we have discussed about the counters and their different types, synchronous and asynchronous. We also discussed about the asynchronous counters in detail. The three instances of asynchronous counters that we discussed were binary up counter, binary down counter and BCD ripple counter. All these counters had n flip-flops which worked in asynchronous manner. That means, the flip-flops used in those circuits did not change their state simultaneously. Rather, they depended on the transition of other flip-flops to which they are connected to. In this class, we are going to see the synchronous counters in detail. Can you guess about the nature of transitions in synchronous counters since you know about the asynchronous ones? The flip-flops in the synchronous counters are always in sync. In other words, their state of change happens at the application of clock pulse, and the same clock pulse is applied to all the flip-flops. The outcome of such a procedure is a uniform change in the state of flip-flops, and the time of such a change is highly predictable. This is an advantage over the asynchronous circuits. But the design of such hardware is little more complex and requires more time and effort. They are expensive too compared to the asynchronous ones. However, let us see how counting both up and down is performed in synchronous counters. The simplest form of synchronous counter is binary up counter. Let us see that first. The logic behind the up counter is at the arrival of clock pulse, the flip-flop at the LSB should be toggled, and this should happen at the arrival of every clock pulse. What about other flip-flops in the circuit? In the asynchronous circuit, their state was decided by the transitions in lower order flip-flops to which they are connected. Here the case is different. The clock pulse is applied simultaneously. So, the logic applied to other flip-flops is they should be complemented if all the bits in the lower flip-flops are equal to 1. The concept will be more clear when we work it out. Suppose we have a 3-bit synchronous counter. For a 3-bit counter, we should have 3 flip-flops in the circuit. Let us call them as F1, F2, F3. F1 stores the LSB and F2 stores the next higher order bit and F3 stores the MSB. Initially, each flip-flop carry a 0 in it. As the first clock pulse arrives, the flip-flop F1 gets toggled and we get 1 there. Now, let us see what happens in the other flip-flops. Remember, the same clock pulse is applied to F2 and F3. What is the input of F2 then? It comes from F1, and what was the value of F1 before clock pulse? It was 0. So, the input to F2 is 0. When the first clock pulse arrives, F2 remains the same, it does not get toggled. Do you know why? As per the logic, the higher order flip-flop is complemented only if all of its lower order bits are 1. Here for F2, it has one lower order bit from F1 and that is 0. So, it will not be toggled. The same happens for the flip-flop F3. Why? The lower order bits of F3 are from F2 and F1. Before the arrival of clock pulse, their values were 0. So, no toggling took place. So, what is the final update? After the first clock pulse, F1 toggles, but F2 and F3 does not, leaving the state of the circuit as 0, 0, 1. Let us proceed to the next clock pulse. Now, the previous value of F2 is 0 and F1 is 1. Can you guess how many flip-flops gets toggled in this clock pulse? Definitely F1 does. What about F2? Consider the rule. The higher order flip-flops need to toggle if all of its lower order bits are 1. For F2, its lower order bit was 1, so it gets toggled. F3 will remain in the same state because its lower order bits were 1 and 0, so the rule is not satisfied. What is the output of the circuit now? It is 0, 1, 0, whose decimal equivalent is 2. See, now you are progressing in counting. Initially it was 0, then in the first clock pulse it became 1 and in the next it became 2. On the application of each clock pulse, we were considering the previous value of the flip-flops. Why previous value? Because the clock pulse is applied to all the flip-flops at the same time, not like the asynchronous circuit where the clock pulse was applied at different timings. So, one flip-flop cannot wait for other flip-flop to change the state. All the flip-flops gets triggered at the same time. That is why the previous value of the flip-flops were considered. Look at the table. The flip-flops that undergo transitions in each clock pulse is given here. Can you state the reason for transition of each flip-flop? Also, if the transition did not happen in flip-flop, can you explain why? For example, what happens when the fifth clock pulse arrives? It will toggle F1 because it is mandatory for the LSB to toggle in every clock pulse. What about F2? Here you need to check the previous value of its lower bits. In this case, it is F1, so check the output column of the fourth clock pulse. There F1 is 1, so now toggle F2. What about F3? Check the previous bit values of F1 and F2. There the values are 1 for both F1 and F2, so toggle F3 and the output becomes 1, 0, 0. Now try on your own and work out the transitions for other clock pulses too. Hope you understood the logic behind the synchronous up counter. Let us see how to design the circuit using the logic gates. Look at the diagram. You can see a 4-bit synchronous counter with 4 JK flip-flops named as FFA, FFB, FFC and FFD connected one after another. The very important point is the same clock pulse is fed to all the flip-flops. The J and K inputs are maintained at high level for the first flip-flop FFA, which is the flip-flop storing the least significant bit LSB. You know that the LSB should be toggled at the arrival of each clock pulse. As per the working of JK flip-flop, when J and K inputs are maintained at high level, it will always toggle the present value. So, that condition is satisfied in the design. Now, what about other flip-flops? The rule says toggle the flip-flop only if all of its lower order bits are 1. How should we ensure this while designing? Take the case of the next higher order flip-flop FFB. It should toggle if FFA has 1 inside it. It does not have to bother about other conditions. This can be ensured by feeding the output of the first flip-flop FFA to the flip-flop FFB. So, the output QA is connected to J and K inputs of FFB. Let's move to the next high order flip-flop FFC. It should toggle only if FFA and FFB have 1 inside it. So, the design cannot be straightforward. To ensure the bits from the flip-flops FFA and FFB are 1, we use an AND gate. An AND gate is inserted before the third flip-flop with inputs as QA and QB, which are the outputs of FFA and FFB. And you know that an AND gate produces 1 only if both inputs are 1. Means when QA and QB are 1, the AND gate will produce 1 and the output of this AND gate is fed into the J and K inputs of the third flip-flop FFC. This ensures that the third flip-flop will toggle only if the first two are at high level. What about the higher order flip-flop FFD? This is the flip-flop which stores the most significant bit or MSB. It should toggle only if FFA, FFB and FFC have 1 inside it. To ensure that, here also an AND gate is inserted with the inputs as output of previous AND gate and the output of flip-flop FFC. When we take the input from the previous AND gate, we are ensuring that the lower order flip-flops are at level 1. So, the currently inserted AND gate produces 1 only if both the previous AND gate and FFC produce 1. The J and K of FFD gets its input from this AND gate. Now, with this design, the 4th flip-flop will toggle only if the first 3 bits are at high level. This is how the synchronous up counter works. Before we wind up the discussion of this counter, please note a very important point about synchronous counters. These counters can be triggered at any edge of the clock pulse. It was mandatory for the asynchronous ripple counter that it should be triggered at the negative edge of the clock pulse. Here, that can be ignored as the same clock pulse is applied to all the flip-flops. So, it could be either positive edge triggered or negative edge triggered flip-flop. Next, we will move on to the counter binary down counter. Now, let us move to the next type of synchronous counter, the down counter. This counter will help you to count down. We had already seen one down counter in asynchronous mode. The same logic is applied here. See the design of the counter given in the figure. This can be constructed by making few changes in the up counter. When we were counting up using the up counter, the output was taken from the Q terminal. To count down, you should take the output from Q dash. The same logic as asynchronous down counter. You are starting from 0, 0, 0, 0 in the up counter and its complement 1, 1, 1, 1 is the starting point of the down counter. To get the complement, we are using the Q dash terminal of the counter. The procedure is same as the up counter. Start toggling at the LSB and the toggling should propagate to the next higher order bit only if all the lower order bits are 0. Look at the figure. This counter is almost similar to the up counter in the aspect that the same clock pulse is applied to all the flip-flops. But the striking difference is the flip-flop's complemented output, which is considered to decide the value of the other higher order flip-flops. Earlier, the output of the flip-flop itself was the decision maker. Notice the AND gates inserted before the 3rd and 4th flip-flop. As in the previous case, here also they are used to ensure that the lower order bits are 0 to toggle the output. Let us work out with an example. Initially, the state of the flip-flop is 1, 1, 1, 1. At the arrival of first clock pulse, the flip-flop at the position of the LSB gets toggled. What about FFB? As per the rule, FFB should toggle only if its inputs J and K are 1. Check the input of the flip-flop FFB. It is the complement of the previous flip-flop's output, QA complement. In this case, it is 0. As you know that if the inputs to J and K are 0, then there is no change in the value of the flip-flop and hence the second LSB will remain as it is. Moving on to the 3rd flip-flop FFC, as in the case of up counter, here we introduce an AND gate. The inputs to this AND gate are QA dash of FFA and QB dash of FFB. At this level, both the inputs of AND gates are 0 and this ensures a 0 input at J and K of the 3rd flip-flop FFC. This makes the flip-flop remain intact and retain its previous value. Now, the 4th flip-flop FFD takes its inputs from the previous 3 flip-flops. They are QA dash, QB dash and QC dash. Again, as in the case of up counter, here also an AND gate is inserted. At present, this AND gate produces a 0 output and ensures no change for the fourth flip-flop FFD. So, after the first clock pulse, the state of the flip-flop becomes 1 1 1 0 and its decimal equivalent is 14. So, you have counted down from 15 to 14. Now, suppose your previous value of the flip-flop is 1000, whose decimal equivalent is 8. What happens then? The LSB gets complemented anyhow and obtains 1. What about the second LSB? Its previous value is 0. So, its complement is fed into the second flip-flop as input. Now, the J and K of second flip-flop becomes 1, which toggles the value. The third flip-flop will receive the input from the AND gate that is taking inputs from the first and second flip-flop's complemented value. The complemented values are 1, so the JK flip-flop toggles the third LSB to 1. The last flip-flop takes the complement of the first 3 flip-flops, and in this case the 3 bits are 1, which produces a 1 at the J and K input of the flip-flop, which toggles its value. In net effect, all the 4 flip-flops toggled its value, producing the output 0 1 1 1 from 1000. So, after this clock pulse, the state of the counter got decremented to 7. What happens when the counter counts down up to 0? Theoretically, it should reset itself and goes back to 15 again. Let us check that case too. Now, the value of the counter is 0 0 0 0. Since all the bits are 0, everything should get complemented to 1 1 1 1. How is it ensured by the logic gates and flip-flops in the counter? The LSB gets complemented at any cost as soon as the clock pulse comes, which turns it to 1. The second flip-flop gets complemented. How? It receives 1, which is the complement of the output of the first flip-flop. As we know, when J and K are at 1, it will toggle its value, so producing 1 as its output. Now, the third and fourth flip-flops also get the same inputs. The complemented output of their previous flip-flops are all 1s, which sets J and K as 1 and toggles its value by producing 1 at each flip-flop. Thus, 1 1 1 1 becomes the next state of the binary down counter when the previous state was 0 0 0 0, or once the counter reaches 0, it resets to 15. Again, you need not have to bother about whether it is positive or negative edge triggered flip-flops. This synchronous binary down counter will work in the similar manner no matter whether it is positive edge triggered or negative edge triggered circuit. Hope you are clear with the concepts of synchronous counters. We have learned both up and down counters in detail. These two counters can be used in any context where up and down counting is needed in digital systems. Let us discuss about a few more synchronous counters in the next lecture. Thank you for watching. See you in the next session. Bye.